This question comes from Priya, who asks, if the Earth suddenly spun twice as fast, with a 12-hour day instead of a 24-hour one, what would actually be different? The first thing to notice is that compared to the scenarios this question is usually grouped with, doubling Earth's rotation is surprisingly survivable, at least at first glance. You wouldn't feel it directly. The planet isn't accelerating, it's just spinning at a constant new rate. You'd wake up, look out the window, and notice the sun was moving across the sky at double its usual speed. Sunrise to sunset in about 6 hours, the stars wheeling past twice as fast. Otherwise, your morning would feel unremarkable for approximately the first few minutes. Then the water would start moving. The Earth's equatorial bulge, the reason the planet is slightly wider at its waist than at its poles, currently amounts to about 21 kilometers. The equator sits 21 kilometers farther from the planet's center than either pole does. This shape isn't accidental, it's the result of centrifugal force pushing outward as the planet spins, and the oceans and land settling into an equilibrium that accommodates it. Double the rotation rate, and the centrifugal force at the equator quadruples, because centrifugal force scales with the square of the speed. The bulge would need to grow significantly to reach a new equilibrium. Oceans respond to this almost immediately, since water is fluid and can redistribute within hours or days. Land responds over geological time, centuries to millennia, as rock flows extremely slowly under pressure. The result of that mismatch is that the oceans would surge toward the equator long before the land could follow them. Equatorial coastlines would experience flooding on a scale that dwarfs anything in recorded history, while sea levels near the poles would drop as that same water migrated away. The Amazon basin, northern Australia, and the island chains of the equatorial Pacific would go underwater. Meanwhile, in the short term, the land beneath them would be undergoing the geological equivalent of a slow-motion earthquake as the crust tried to catch up. The weight effect is real, but modest. Right now, because of the existing centrifugal force and equatorial bulge, a person standing on the equator already weighs slightly less than the same person standing at the poles, about 1 part in 200. Double the spin, and that reduction roughly quadruples, so equatorial residents would weigh about 1.4% less than their polar counterparts. Not enough to notice without a scale. Not enough to float. The atmosphere is a different matter. Earth currently has 3 large circulation cells in each hemisphere: the Hadley cell in the tropic, the Ferrel cell in the mid-latitudes, and the polar cell, which organize global wind patterns, determine where deserts form, and drive the trade winds and the jet streams. These cells exist at their current size because the Coriolis effect, the deflection of moving air caused by Earth's rotation, limits how far poleward the Hadley cell can extend before breaking down. Double the rotation rate, and the Coriolis effect doubles, and the Hadley cell narrows toward the equator. The 3-cell structure would be squeezed into more bands, each covering fewer degrees of latitude. Jupiter, which rotates in just under 10 hours, has 8 distinct atmospheric bands in each hemisphere rather than 3, and you can see the result with a backyard telescope. A faster rotating Earth wouldn't reach Jupiter's extremes, but global circulation models run at double Earth's rotation rate suggest the atmosphere reorganizes into more, narrower bands with stronger and more persistent jet streams. What this means on the ground is a wholesale redrawing of the climate map: drier region, pushed closer to the equator, wetter bands in different places, trade winds intensified, and storm systems more tightly constrained in their tracks, but potentially more energetic within those tracks. There's one more consequence that would be felt almost instantly, and it has nothing to do with weather or sea level. Every geostationary satellite in orbit, the ones that sit in a fixed point above the equator and handle most of the world's television broadcasts, weather observation, and a large portion of its telecommunications, would immediately be in the wrong orbit. A geostationary satellite works by orbiting at exactly the speed the ground beneath it rotates. Move that ground faster, and the satellite is now orbiting too slowly to keep up. It would appear to drift westward across the sky and eventually become useless for its intended purpose. Replacing a geostationary satellite fleet requires years of launches and billions of dollars. All of that infrastructure would go dark on day one. Earth, in its early history, actually rotated much faster than it does today. When the moon formed, roughly 4.5 billion years ago, a day is estimated to have lasted around 6 hours. Over billions of years, the moon's tidal forces have been gradually slowing our rotation by transferring angular momentum outward. The moon drifts about 3.8 centimeters farther from Earth every year as a result, so a faster spinning Earth isn't science fiction. It's just deep history. The life that eventually emerged did so in a world that was already slowing down, and it has been adapting to a lengthening day, very slowly, ever since. What doubling the spin would reveal is how precisely tuned the modern world, its coastline, its climate, its infrastructure is to the specific 24-hour rate we've inherited. Not because 24 hours is special in any cosmic sense, just because that's what everything grew up around.